Hello, my name is Arben Kalziqi with the Wolfram U team here at Wolfram Research, and this is a whirlwind introduction to the basics of neural networks in Wolfram language. By way of an introduction, I think we should cover why neural networks are getting popular again over the last few years here. So we have a lot more data available, sensors are cheaper, we have a lot of bandwidth, we have more applications than ever for neural nets, and we have a ton of user-generated data coming from the internet. Our hardware has improved so we can train larger networks faster, and we have more specialized network architectures. Neural networks are already in use for computer vision, machine translation, speech-to-text, sequence prediction, and things that you might commonly see referred to as AI. Wolfram language provides a really neat toolkit for dealing with neural networks. It allows you to easily create encoders and decoders to represent the layers in your network symbolically and extract and work on them symbolically. You can also use different formats to import and export your nets. There's also a bunch of prepackaged datasets that you can use for training, as well as neural nets that you can modify and retrain yourself. Here's a quick outline of the topics that we'll cover today. We'll get started by talking about tensors, which are really just collections of numeric objects. We'll talk about encoders and decoders, and these are ways that we can convert, say, images, text, sound, and so on into these numeric objects. And then the decoders will let us transform the tensors, the numeric objects, back into things like images and text. Neural networks are made up of layers, which are the things that actually do the computations on these tensors. We'll talk about how you can compose these layers either as simple chains or more complex graphs. We'll talk about how you train these networks and about some different supervised learning applications of these networks, as well as how we gauge how well the network is doing, which we do with loss functions. And finally, we'll do a worked example from beginning to end of training a network using NetTrain. So the first thing to mention here are these tensors that I mentioned. In the context of neural nets, at least, you can think of tensors as just rectangular arrays of numbers. A rank 1 tensor means that you just need one index to describe the position of any particular element, like a vector, so 1, 2, 3. Rank 2 tensors you can think of as matrices, and you can have higher rank tensors as well. Here are some examples of tensors to really drive the point home. So you can think about vectors, or as we just said, 1 tensors, as representing geometric points. Like here, we have these points on the plane, and these all have a dimension of 2. They are 2 numbers that specify some place in a plane. A vector could also represent, say, a class, a categorical variable. So in this case, A refers to the first index, B the second, and C the third. You can kind of think of these as unit basis vectors. So the more you are in this direction, the first direction, the more A you are. The more you are in this direction, the more B you are, and so on. A simple matrix, a 2 tensor, can represent a grayscale image. Each number here just represents a brightness. And of course, if you have more information, like in an RGB image or any other color space, you can represent that as a 3 tensor, which you can think of as a collection of matrices. Okay, that's all well and good, but how do we actually get our input data into this numeric form? And once we have a numeric form, how do we get it back into some readable data, like an image or a class? That's where encoding and decoding comes in. So it is the case that sometimes your data might already be a numeric tensor, but generally speaking, it's not. In cases like those, you want to use a net encoder to handle the job of converting your data into a tensor. A net encoder in Wolfram language just acts like a function. So we can define here a net encoder enc, which takes in an 8x8 grayscale image, and you can see its action on an 8x8 grayscale image here. It converts it into this numeric tensor. An encoder can also encode discrete classes, in this case, cat, dog, and frog, as the unit vectors we mentioned before. And you can see here that if we were to encode, say, frog, we get 0, 0, 1, because frog was the third element of this list. So similarly, if we were to do cat, we would get 1, 0, 0. And you can see that here as we map the encoder over these different labels. We get these different unit vectors back. A net decoder does the opposite job and will convert these vectors back into their categorical class labels. Next up are layers. So layers are the fundamental building blocks of a net. They represent simple operations on numeric tensors that produce other numeric tensors. They can take one or more inputs, return one or more outputs. It's basically just like a function of an arbitrary number of inputs that outputs an arbitrary number of outputs. Some layers contain learned parameters, and these are the things that are tuned when you train a network. Most layers just take one input and return one output. That is one input tensor and one output tensor. Those tensors can have arbitrary dimensions. Layers can be combined in a few different ways. Namely, they can be combined into a linear chain or a more complicated directed acyclic graph. Let's look at some examples of layers. Probably the most basic example we can start with is a linear layer. Linear layer you can basically think of as a matrix operation that multiplies its input vector and then adds some bias vector. So here you can see the operation of a randomly initialized linear layer on the two vectors represented by the points in this plane. It transforms these points into the points you see over here. Now, the specific shape of this is not really relevant because it's randomly initialized, like it says right here, but the point is just that we are taking in some vectors here and we're transforming them into new vectors here. Now, it doesn't have to be the case that a linear layer transforms some input to some output with the same dimensions, but in this case, that makes it easy to visualize. Another basic layer that we can talk about is the elementwise layer, and it does what it says on the box. It applies some function to each individual element of a tensor. Typically, this function is used to add some simple nonlinearity. Now, we can see the effects of some of these elementwise layers here. For example, we could ramp inputs, cut everything off that's negative, and then keep everything that's positive. Or we could rescale using a logistic sigmoid or a tanh function. These are just some common functions that are used. A slightly more complicated example of a layer is the convolution layer. Now, these are quite useful in that these are what enabled neural networks to really start dealing with computer vision tasks. The idea here is that this is looking at a rank 2 tensor, but generally speaking, since images might have color, it works with a rank 3 tensor, but the idea is the same. You can look at some collection of pixels here and then convolve them with some kernel to some smaller dimension. And something that's neat is that these kernels are what you learn during training for a convolutional layer. So just like a linear layer is learning its weights and biases, a convolutional layer is learning these kernels. And for certain convolutional networks, you can visualize these kernels, and these loosely mirror the response of neurons in the visual cortex. So how do we compose these layers? Well, the simplest way to do it is with a net chain. This is just a sequence of operations. Each operation is represented by a layer, and basically what happens is that each layer takes some input from the previous layer and feeds some output to the next layer. So here's a simple example of one of these net chains. You have some input, it gets fed to a linear layer, the output of the linear layer gets ramped with the elementwise layer, and then all the outputs of the elementwise layer are summed up with a summation layer. And we can see that here in the structure. And what's neat is if you click any of these, you get more information about what each individual layer is doing. We can see here that this network is uninitialized, which is helpfully highlighted for us in this red color, because we haven't yet assigned any weights and biases to this linear layer. That is, if we think about the matrix operation, we haven't yet defined the elements of the matrix. We just know that it has a particular size. That's all. So if we want to think about what's going on here, we start with some input. A linear layer is applied, and it creates a vector of length 5. Then, that vector of length 5 is fed into the elementwise ramp, and that outputs another length 5 vector that has its components modified. Finally, the resultant vector is fed into a summation layer that just adds up the components of that vector and creates a scalar. In this case, that scalar is the output. Here's kind of an example of a net chain that you might see out there in the world. A simple example, a multi-layer perceptron. So what we have here is a chain that takes in a scalar as its input. Then it applies a linear layer to create a length 5 vector. It uses tanh on each of the components of that vector. And then it combines those five components into a scalar output, again using a linear layer in this case. And again, we can click on this to see. But the point is really just that if we initialize this net with some random numbers, we kind of fill out the linear layers here with some random numbers, we can see what this net is doing to inputs. Say if we take inputs from -5 to 5, we can see its action on this. So it takes in a scalar, it outputs a scalar. It basically is just a function. And just kind of a useful hint here, linear layer and element-wise layer are so common that we have a little bit of syntax sugar here where if you just write 5 or if you just write a single function, if you write just a scalar or a function name, it will be assumed that the scalar represents a linear layer and the function represents an element-wise layer. Next up are graphs. So net chains are kind of an easy way to get started with understanding how neural networks work, but neural nets wouldn't be so useful if it was just one layer goes to the next layer, goes to the next layer, goes to the next layer in a sequence, and that's it. Generally speaking, it's really useful to be able to combine these layers in more complex ways, represented by a graph. So this is kind of a serious example, but here we have a very complex piece. Each of these little dots represents a layer, and these things are all connected in a rather complex way. Here's just the way that you input these things. Basically, you specify what layers exist, and then you specify their connectivity. If you're used to talking about graphs, you can think about this as a list of vertices, which are the layers, followed by a list of edges, which are the connections between those layers. Let's look at an example of these. So in this example, we want to take some scalar input, and we want to apply 2 separate transformations and then output the results, both results. So here's our graph. We specify our layers. Remember, these are linear and element-wise layers. And then we specify the connections. The first layer goes to the second layer, goes to the third layer, and so on in each case here. So this is one set of connections, and this is another set of connections. And we specify some properties about the inputs and outputs. And we can really see what's going on here in this visualization. So with a net graph, we can see the structure, what's happening. We can see we have an input, goes here, has an operation applied. There's an operation applied to the output of this, and then this goes to 2 separate places, and they have 2 separate operations applied, which produce 2 separate outputs. And just like with the chains, you can click on any of these individual layers to get more information. If we were to, again, randomly initialize the layers there, we can see what happens when we apply the net to just one scalar input. We get 2 scalar outputs, named y and z, is what we chose to name them in the graph structure. And we can plot these as well. So if we just feed some range of scalar inputs into this net, we get some range of scalar outputs, 2 of them, in fact, y and z. Now, for the purposes of visualization, we've been randomly initializing these nets. But of course, in the real world, you don't want to have randomly initialized nets. You want to have trained nets. And for that, you need training data. So that is how neural networks learn. So we can think about this training data as sort of implicitly specifying some sort of function. And what the training does is it tunes the net to approximate this function. So something neat in Wolfram language is that there's a lot of training data that's just built in for the sake of an example. So you can use resource data to get several different data sets, which we'll be using below. There are also quite a few different data sets that are accessible here, but you can find those on your own time. A very popular one, of course, is MNIST, which is a set of handwritten digits and then their actual labels. This is just used for kind of the OCR of digits, optical character recognition. So we can pull in the MNIST dataset here, and here's what a random sample of that looks like. We have a handwritten digit and then the label, handwritten digit and then the label, and so on. Here's another one, CIFAR10, which just has some rather small images, and then they have some labels. There are 8 labels in this dataset. You can see with this random sample. CIFAR 100 is a little bit more complex. The idea here is that each image has 2 labels. It has kind of a larger class label and then a more specific sub-label. So here, this image is categorized as fruit and vegetables, and then more specifically, it's an apple. Here, this might be a household electrical device, and then more specifically, it's a telephone. So training data can take many forms. It's often the case that you want a neural network to do some sort of classification, but just as often, it's the case that you'd want a neural network to be able to predict some numerical value. So the idea here is basically your neural network performs something like a fitting operation. You start with some input, and the neural net wants to compute a prediction of what the output should be. In cases like this, your training data should consist of XY pairs. And it's worth it to note here that Wolfram language does have a built-in function which does this called predict. And oftentimes predict will just work a little bit better than trying to cook up your own neural network. But you can absolutely create your own neural network and train it with your own data for specific use cases, or if you have some sort of particular use case in mind which doesn't fit predict. As for classification, this is a very common task for neural networks. This is something that's very frequent in machine vision, for example. The idea is that you have some distinct classes. And what the net does is when you feed it an image, it computes some probability distribution over the classes such that the probabilities all sum to 1. So what you want to do here is use something like a softmax layer. A softmax layer at the end will turn your net's kind of arbitrary vector output into a vector of normalized probabilities. So you can see here, maybe my output vector has these different values. What the softmax layer is doing is it's converting these arbitrary values into a normalized probability. So once you have these probabilities, the idea is that you want to decode these probabilities back into classes, right? If you feed your neural network an image and it just outputs some probability vector, that's not so useful. What you really want is an actual label for the thing that you've put into the network. And that's where a decoder comes in. So let's make a simple decoder that has 3 classes, dog, cat, and frog. And the way this works is that if you feed this a probability vector, by default, it will just return the class that has the highest probability. So these 3 values you can kind of think of as axes in probability space. And the axis that has the highest value on it here is dog. And here it's cat. Now, decoders have various other properties that you can use just by typing in the second argument space here. So you can feed it this probability vector right here and ask for the probabilities of each, and it will just give you the probabilities for each class. You can also ask about the entropy of the prediction. You can ask about the top 2, top n probabilities, or the probability for a specific class. And just as an encoder gets attached to the beginning of a net, a decoder can just be attached to the end. That way, you can go from your image or whatever it might be to a tensor, do all your operations with your layers on your tensors, and then at the end, what you get back is not some crazy vector or tensor. What you get back is just a nice label. When you're training your network, you need a way for the network to determine how good a job it's doing of predicting the actual outputs. This is where a loss function comes in. A loss function is a way for the network, when it's making these predictions, to compare those predictions to the true results. The specifics of how you compute the loss are kind of dependent on your problem and your network structure, and we'll talk about that a little shortly. But when you're training with NetTrain, the loss will be shown on a plot like this. And you can see typically what happens is that the loss will decrease very quickly to start with, and then as you approach a more optimized set of parameters, the loss will plateau a little bit. And you can always manually stop your training if you notice that the loss is plateaued too hard and training isn't really doing much good for your network anymore. Like I mentioned, different tasks kind of call for different loss functions. There are a couple of these built in, well, more than a couple, but a few of the simple ones that are frequently used here are the mean absolute loss layer, mean squared loss layer, and cross entropy loss layer. So you might notice they all have loss layer attached there. So as you might also notice, these things are all layers. So the loss functions are also layers that you can put into your network. If you don't choose a loss function, NetTrain will automatically choose some appropriate loss functions for you, but you can build them directly into your net and use whatever loss layers you like. Something that's a little bit unique about loss layers is they're not taking just one input, which most layers are. They're attached to the output, so they take the output, and then they also take in, as an input, the ground truth from the training data. That's how they compare. Here's a visualization, an example of some loss functions. So for regression, you might want to use something like mean absolute loss or mean squared loss. This is just a visualization of mean absolute loss. Basically, what the network is trying to do is it's trying to minimize these little errors here. So it's trying to form a prediction for this data which minimizes the error. This can result in a problem known as overfitting, where basically, instead of having this nice prediction for this data, your prediction might be this curve, this wild curve that goes through all the points in an attempt to minimize the error a little bit too much. You can kind of think of this as teaching to the test. It just memorizes all the answers and that's it. So that's the thing you need to avoid when training your networks. Let's look at a few examples of how this works numerically. So suppose we have some loss layer and it's just a mean absolute loss layer. If we give it an input and a target, we can see that here, what's being done is it's computing this error based on the difference between the input and the target, and then it's taking the mean. So it's just the absolute value of the difference between these two vectors and then the mean of those absolute values. And we can see that if we just actually make this computation with the vectors, mean of the abs of the difference between these two vectors. So the point of this demonstration here is really just to show that despite being part of this, maybe a little bit esoteric sounding mean absolute loss layer, it's really just a simple functional operation that's all bundled up into one little layer. Now, when you're dealing with predictions which do not have a numerical output exactly, like classification, you might want to use a different type of loss layer. What's usually used for classification is the cross-entropy loss layer, which computes an information theoretic distance between your class distribution from the net and the real distribution from your data. I think this is a little bit easier to see through an example, so let's have an example here. If we have an index-based cross-entropy loss layer like this, let's say we feed it an input where we have 1, 0, 0, and the target is 1. So this target 1 here is an index, which is saying that ideally what we want to have is this unit vector, which is just all in the first component here. So the loss here would be 0. Similarly, the loss here would also be 0 because here it's all in the second component. Now, if we were to have a target of 1 and we have most of the vector here, most of it concentrated in the first component and a little bit in the other two, we get a small loss. Here, however, when we have a target of 2, but most of the vector is concentrated in the first component, we get a larger loss. So the basic theory for training a network is that you find some local optimum for these learned parameters by minimizing the loss. An easy way to think about this is with the linear layer. Remember that you can think of a linear layer as a matrix that multiplies an input vector and then adds another bias vector. So what the optimization process is doing is it's picking out the components of that matrix and of that vector. Minimizing the loss corresponds to finding weights for the net that cause it to predict the output as well as possible. That is to say, training the network is really an optimization process. Training data is split into a few batches, and on each batch, NetTrain will compute the error of the network in reproducing the true output. And from that, it can calculate a small change to the parameters which will make the network perform a little bit better. By doing this over and over, the net will converge on sufficiently good values to accurately predict outputs. This process is called gradient descent. It's worth noting here that training time is highly variable because it depends on the amount of training data you have as well as the structure of your network and how many parameters it has. Completing a single round of training, i.e. going through all of your training data one time, could take anywhere from milliseconds to hours. Let's put all of this together into kind of one complete example. We'll use the CFAR10 object image database that we mentioned before as our training data here. So recall that this is just a bunch of images with labels. So this is a truck, this is a deer, this is a dog, and so on. The first thing we want to do is just get a collection of the different possible classes, like truck, deer, dog, and so on. So we do that by just deleting all the duplicates from all these labels, and we get this list of classes here. We can then just make a net decoder of these classes. And what this net decoder will do is it will decode probability vectors back into these class labels. Now, if we want to be able to deal with these images, we need to convert them to tensors. So for that, we'll use a net encoder. Here, this net encoder takes 32 by 32 images, and we get all the extra information here about this encoder. Now, we're going to use our net chain to combine a bunch of different layers. This is a computer vision task, so it's going to be using those convolution layers that we mentioned before. Again, notice the syntax sugar short versions of linear layers and element-wise layers here. And for the output, we have our decoder, and for the input, we have our encoder. So our network looks like this. We take an image as our input, we encode it into this tensor here. We have 32 by 32 and then the 3 for the 3 color channels. Then we have these convolution ramp and pooling layers, kind of 2 stacks of these things. And what these things are doing is they're changing the spatial structure. So we start with 3 by 32 by 32. We use this convolution layer here to get 20 by 28 by 28. And as we go down, we're changing the structure. Eventually, we flatten the structure out entirely here, so we just have one big long vector. We've removed all the spatial information. And then we use a linear layer and a ramp to kind of compress this length 1250 layer to a length 10 vector, which we then normalize with softmax layer to get a vector of probabilities for each class. Then that vector is decoded with the decoder, and we get a class, which will be our prediction for what's in the image. Now, I won't train the network live since it takes a couple minutes, but we just say net train, we give it our net, our training data, and we can specify a max number of training rounds. Here's just a screenshot of what this looks like. And now if we apply our network to a list of images, we can see that this first one is guessed to be an automobile, a frog, an airplane, a bird, and a horse. So it's gotten these all correct, at least. And the network, you can use all those decoder properties we talked about before. So you can get the top probabilities or the probability for any particular thing, and so on. So it didn't do too good a job here. It thinks it's more likely that this is a dog than I think it's an ostrich. But, you know, it's a 32 by 32 image. It's quite small. Now, once you have a net, it can be really useful to measure how well it's actually doing. So what we can do here is we can pull in some test data. This is data that the net has never seen. It's only seen the training data from this resource object. We can take the function classifier measurements and use that on our trained net with the test data here. And we get this nice plot, this confusion matrix. Along the diagonal, what we have is all of the times that the network correctly predicted the class of an image. And then on the off diagonals, we see where it has predicted things incorrectly. So here, for example, it predicted an automobile, but actually it was an airplane. And here, for example, it predicted a truck, and it was actually a ship. So you can get the overall accuracy, among other properties of this thing. And here, it's not so accurate. Some more training, some higher quality training data, more training data. There are various ways to get a more accurate network here. And we can see here other properties like the worst classified examples. Here, the 10 worst classified examples. And what this tells us are the examples from the test data where the predictions, the probability vectors for these images from the network were just totally off comparatively. They're the examples that have the most out of whack probability vectors. They have the highest cross-entropy loss. You can also find out, this is quite useful in many contexts, which examples are the most confusing for your network. Ours has gotten confused about the differences between cats and dogs, between automobiles and trucks, birds and cats, deer and horses, and dogs and horses. And frankly, for a network that's dealing with 32 by 32 images, I think that these are pretty reasonable confusions. And here we have a list of useful references for neural networks and machine learning more generally. I know that this was a whirlwind introduction as promised, but if you go back and check out this notebook on your own or pause on any particular slide, I think you'll find that there's a lot of detailed information here that should be helpful to you for understanding the basics of neural networks in Wolfram language.